Hello everyone. So today let's solve the problem number 787, cheapest price for the K stops, right? So let's go with the this one question. Let's see what the question states here. We are given n cities connected by the flights. Yeah, you can clearly see here. We have been given n cities connected by the flights, each with a cost. So these are the cities directed graphs 0 to 1. City 0 is connected to city 1 with a cost this one 100 actually, right? So n cities connected by the flights actually 0 to 1. The flight is going from the source nothing but 0 to the destination 1 with a cost 100 with a cost 100. Yeah, so that's what they have given here. That's what they have given here, right? So this is nothing but the cost. So flight is going from this source to destination. Actually, I can just call this one as source and this one destination, just for the example. So same goes with the 2 to 0, 1 to 2, as well as 2 to 3 and 1 to 3, right? Yep. Next, we must find the cheapest price from source to destination with at most k stops, right? So if it is impossible, then we have to return -1. If it is impossible to -1, again we have to find the cheapest price. Just remember, from source to destination with at most k stops, right? With at most k stops, right? So here, I hope the question is clear. Let's do one thing. Let's hop into the approach part directly. Let's hop into the approach part directly. Let me consider the same first example for the approachment here. Just give me a second here. Yeah, let me consider same first example for the approach. So we can just go with the Dijkstra's or Bellman Ford. It works. It works. This one. Previously we had solved the problem on the Dijkstra itself, I believe. So let's go with the BFS or the modified BFS, right? Similar, very similar to the this one Bellman Ford like structure, but it's not completely Bellman Ford. We'll be going with a modified BFS here. Right, let's consider the first example. So that I'll just leave you to do the same thing by considering the second example. Right. So I'll just consider first example here. First, what we will be doing again, as I've said, we'll be going with a modified BFS or the BFS to solve this problem. K, we have been given 1, meaning we can go with only one stop, right? From the source to destination, there should exist only one stop, right? So destination we have been given 3, source we have been given this one. So this is the source and destination is nothing but the 3. Destination is nothing but the 3, right? So this is fine. First, what we'll do, we'll build a graph. So they have already shown the graph. I don't have to write the graph, right? So this is fine. Next, we will start from the city 0 with a cost 0, right? Initially, we'll start from this one, city 0, and with a cost 0, right? So level 0. First, let's consider the level 0 here as we are going with the BFS. From the city 0, we will be going to the 1. So this 1, right? From the city 0, we will be going with the this one, right? City 1 actually with the cost 100, with the cost 100. Yeah, so from level 0, this one, from the city 0, we will be going to the this one, what do we call, 1 second, from the city 0 we will be going to the city 1 with the cost 100. Yeah, so this is fine. And level 1, what we will do, so there exists one stop actually. From city 1 we will go to 3. So this one we can just go to this one directly, right? So from city 1 we can just go to this one, city 3 directly. So this will cost actually 100, the previous one. So this level, level 0, 0 to 100 plus 600 with one stop. So this will be considered as one stop actually, 0 to 1, right? So 1 we have stopped this node. This is considered as one stop. So from 1 to 3, we will move from 1 to 3 with the cost 600 actually. Total from 0 to 3 with one stop, right? So we are moving with one stop actually. So this will be 100 plus 600, right? 100 plus 600, which will lead us to the output 700 actually, 700, right? So this is one thing. And also you can note down one thing here. We can just go here 0 to 1. So this is fine. Then we can just go to this one 1 to 2 and 2 to 3. But here stops will be, so this is one stop, 0 to 1. We have to stop at 1. 1 to 2. So this is one stop. This is one stop. It is the second stop actually. This is considered as one stop as well. Then we will be moving on with going to 2 to 3 actually. So there are two stops here, there are two stops instead of the one, there are two stops here, right? So this 1 and 2 are considered as the stops itself, right? So there are two stops. We cannot go beyond 1. K we have been given 1. We can go with at least this one. Maximum one stop actually, right? So we have got the output 700. So we can just consider 0 to 1, 1 to 3 directly. Yep. So yeah, minimum cost to reach 3. Minimum cost to reach 3 from the source 0 is nothing but 700. Is nothing but 700. Very simple, right? So we will be using BFS to write the code. So now we are having complete idea of the problem, right? So let's do one thing. Let's quickly discuss the complexities part as we are completely familiar with the approach part, right? So what will be the time complexity here? Time complexity would be big of K into E. Time complexity would be big of K into E. And what would be the space complexity here? Space complexity would be big of B plus E, right? So the time complexity would lead to big of K into E, and the space complexity would lead to big of B plus E, right? So time complexity would lead to big of K plus E, right? So each edge may be relaxed up to K plus 1 times in BFS levels here. Each edge may be relaxed up to K plus 1 times in the BFS levels, right? So overall time complexity would lead to big of K into E. And what would be the space complexity here? Space complexity would lead to big of V plus E as well for storing graph and queues, right? So the time complexity and the space complexity for the code that we'll be writing in the future would be big of K into E plus V plus E respectively, right? So this is fine, I believe. So yeah, now as we are completely familiar with the approach as well as the complexities part, we are good to write the code. Let's start writing the code. So first thing here, let's create the adjacency list to represent the graph. So I'll just go with map here, integer my list of int. So this is fine. Yeah, so I'll just go with that graph equals new hash map. So this is also fine. The next step would be, let's go with a simple for loop here for int f of flights actually. So within the for loop, I'll just go with graph dot compute if absent, right? Compute if absent of f of 0. This is also fine, comma x new array list. So this is fine, new array list. So I'll just go with add of new int. Mm, yep. So this is fine. Uh, f of 1 comma f of 2, f of 1 comma f of 2, right? So I'll just come out of this one entirely. So yeah, let me come out of this one entirely. Next step, we have to, or as we had discussed earlier, we'll be making use of the BFS, right? So, and BFS uses queue. We know this one. Yeah, each element stores city, cost, as well as the stops accordingly with the question. Yep. So I'll just go with here queue int. So this is fine. Queue equals new, sorry, linked list. So let me make this one capital L, or else we'll be getting there. Yeah. So new linked list. Why did I leave space, Yaman? So this one has to be linked list as we are making use of the queue here. We can go with the array DQ as well. So let's go with the linked list itself for this one. So I'll just go with add, yeah, new int. So what shall I go with initially? Source will be starting with a 0 with a cost 0, right? So we'll be starting with a 0 with a cost 0. We have already discussed this one. Source will be start the source. We are starting at the 0 level 0 actually with a cost 0. That's what I have written here. So this is fine. Next, let's do one thing. Let's track the minimum cost to reach each city to avoid the unnecessary visits, right? So first, let me initialize min cost here, right? Let me initialize min cost equals new int of size n. Yep, so this is fine. Yeah, so I'll just go with arrays dot fill of min cost. I'll just go with integer dot max value, integer dot max value. So finally, let me go with minimum cost of SRC of SRC. Let me assign this one to the 0. Yeah. Next, let's go with a BFS traversal, man. Next, let's go with a BFS traversal. So I'll just go with while of not 2 dot is empty. So this is fine. So within the while loop, let me go with current here. So this one q dot poll. Yep. So this is fine. Let me initialize city to current of 0. Let me go with cost equals current of 1, and also the final one here stops equals current of 2, right? So current of 2. So next what I'll do, if stops exceed the limit, then we have to skip, right? So if I'll just go with stops, if it is greater than k, then we have to wait, obviously skip, right? So we shouldn't consider that one basically in simple terms, right? So I'll just give the continue keyword, right? So now let's explore all the neighbors, man. Yeah. So this is simple. I'll just go with a graph dot contains key of city. So this is fine. Let me go with a for loop here. Int next of graph dot get of city. Let me pass the city here. So let me go with next city here. Let me go with the next city. Let me assign this one to the next of 0. Yeah, I'll just go with the next cost actually. Next cost. So this will be cost plus next of 1. Cost plus next of 1. Right. So the final one, if we found a cheaper way to check the next city, then we have to consider that one as well. Right. So I'll just write the simple if condition for that one. I'll just go with the next cost here. If of next cost, if it is less than minimum cost, right? So where is min cost here? Let me copy this one. Let me paste it over here. Min cost of next city. So let me copy this one. Let me paste it over here, right? So within the if condition, so min cost of next city we have to consider, right? So I'll just go with min cost here of next city. So I'll just go with next city. This is fair, and let me set this one to the next cost actually. Let me copy this one and paste it over here, right? Also, now let's add that one. Yeah, I'll just go with the q dot add new int. So this is fine. Let me go with next city, next cost, stops plus 1. Next city, oh yeah, this is fine. Along with the next cost, so this is fine as well. And let me go with stops plus 1, right? Stops plus 1. So, yep. Yeah, this is fine. Yep. So, finally, we are left with only one thing here. We are left with only one thing, nothing but if the destination city cost is not updated, then we have to return -1 in that case, right? So I'll just accordingly with the question, they have strictly mentioned this one in the question, right? So I'll just go with min cost somewhere I have used. Let me copy this one. Return. Let's return the min cost of destination. If it is equivalent to integer, I have used the integer dot max value. So let me copy this one entirely. So yeah, let me paste it over here, max value. Then I'll just we just have to output -1 in that case if it is not possible. Else we have to go with the min cost of destination itself. Yeah, I'll just go with min cost of destination. Yep. So this is fine. Simple one, man. Yeah. This problem is actually simple one. Yep. So this is fine. Let me hit the run button. I hope this works, man. We have error here. So this C has to be capital. Line number 16. So this is fine. Yeah, the C has to be capital. First, let me change this one. Minimum cost. Line number 32. Did I give here min cost? Yeah. So I'll just go with the capital C. Let me run this one again. Yeah, the sample test cases are getting passed. So let me hit the submit button quickly, man. Hope the solution, I mean, I hope it passes for all the test cases. Yeah, all the test cases are getting passed, right? So whatever the code that we have written works absolutely correct for all the test cases. This is pure BFS, man. If you know the this one, if you know how to implement the BFS, that's fine. That's well and fine. Only BFS is required. And if you know the Dijkstra's or the Bellman-Ford, you can implement Dijkstra's and Bellman-Ford. Dijkstra's basically uses the priority queue. So you can just go with the Dijkstra and you have to just relax the nodes at the end. That's what, right? That's what you have to do. And the same thing you have to do with the Bellman. Bellman-Ford, this is almost similar to the Bellman-Ford itself, right? So the code, this one, we are making use of the BFS, and it's if you know the algorithm, this is completely similar to the Bellman-Ford. We have made use of the we can just call this one as the modified BFS instead of the BFS, right? That's almost similar to the Bellman-Ford itself, right? So this is fine, I believe. I hope the solution part is completely clear along with the approach and the complexities part. For now, this is it. Thanks for watching, guys.